Welcome to the Explainer. Okay, let's just dive straight into what honestly feels like the ultimate algorithmic cheat code, prefix sums. Now, our mission today isn't just to memorize some mathematical formula. We are going to completely rewire how you see problems. We want to train your brain so that whenever you encounter range sums, frequency accumulations, or repeated calculations, it just automatically triggers the prefix sum pattern.
Here's our roadmap for this explainer. 1. The core intuition. 2. Avoiding common indexing errors. 3. Prefix sum plus hash map. 4. Spotting the hidden patterns. And 5. Advanced dynamic range queries. We're moving systematically from the basics all the way to FANG-level combinations.
Section 1. The core intuition. Let's talk about eliminating the waste of repeated work, which is really the whole point of this algorithm. Think about it. If you're checking every possible subarray and adding them up from scratch every single time, you are creating massive, wasteful, nested loops. It's like checking a bank account history, right? If someone asks how much you spend between Tuesday and Friday, you wouldn't track down every individual receipt for the entire week and tally them up one by one. No way. You just take your total balance on Friday and subtract your balance from Monday. That simple, everyday logic is exactly what we're applying to our code. And this perfectly illustrates why we use this pattern. Instead of moving at a snail's pace through nested loops and hitting an O of n squared time complexity, we can literally launch our performance like a rocket. By pre-computing our history, we trade just a tiny bit of space to completely eliminate an entire nested loop. We do the heavy lifting exactly once in O of n time, and suddenly, boom, every single query after that drops to instant O of 1 constant time. So the crucial takeaway here is that we are converting repeated calculation work into an instant answer just by pre-computing our history. Imagine an array like 2, 4, 1, 5, 3. You just build a parallel array that holds the running total at each step. By storing these partial results, we can visually prove that the sum of a specific range is literally just the total at the end of the range minus the total right before the range started. It's just a single elegant O of 1 subtraction. Section 2. Avoiding common indexing errors. This is the non-negotiable n+1 rule. Let's get into the implementation to avoid the absolute biggest trap candidates fall into under interview pressure. Take a look at that leading 0 in the prefix array row. This is huge. If your original array is length n, your prefix array absolutely needs to be length n+1. Initializing this array with a 0 perfectly handles any queries that start at the very beginning, index 0, of your original array. By intentionally using that leading 0, this exact formula works universally for every single range. Prefix at j+1 minus prefix at I. You'll never hit a nasty out-of-bounds error, and you don't have to write any messy conditional if statements just to handle edge cases. It just works. Remember, missing that leading 0 is literally the #1 source of bugs in prefix sum solutions. It leads directly to off-by-1 errors that can easily tank an otherwise great interview. Make it muscle memory. The second you realize you need a prefix sum, just write out an array of size n+1 with a 0 at the front. Okay, moving to section 3, prefix sum plus hash map. This is it. This is the ultimate interview combination, and a pattern you absolutely have to master. Let's tackle one of the most frequently asked medium difficulty problems out there. The prompt asks you to find the total number of continuous subarrays that equal a specific target, k. Here's the trap a lot of candidates fall into. They immediately jump to a sliding window. But you can't use a sliding window here if the array contains negative numbers. Why? Because negative numbers mean the sum can actually decrease as your window expands. That completely shatters the sliding window logic, which means we need a totally different trick. The real trick is combining our prefix sum with a hash map. We're basically taking the classic complement lookup logic, like you'd use in the two-sum problem, but applying it to our cumulative totals instead of individual elements. As you iterate, your current prefix sum minus your target k gives you the earlier prefix you need to find. If that earlier prefix already exists in your map, guess what? You've just found a valid subarray. But here is the critical pitfall you have to watch out for. You absolutely must seed your hash map with 0 mapped to 1. Why? Because if your current running sum perfectly equals your target k, your target complement formula is going to result in 0. If you don't preload 0 into your map, your code is just going to fail to count that valid subarray. And trust me, interviewers will absolutely catch it. Section 4, spotting the hidden patterns. This is your detective framework for interviews. How do we instantly know when to pull this specific tool out of our algorithmic toolbox? As the source material points out, coding the actual solution, that's the easy part once you know what to do. The real skill, the thing that actually gets you the job offer, is recognizing the underlying clue within the first 60 seconds. Nobody is going to hand you a prompt with a giant neon sign that says, "Use prefix sum here." You really want to follow this exact timeline in your interview. Classify the problem pattern by minute 2. State your optimization out loud by minute 4, saying something like, well, since we need frequent range sums, a prefix sum will drop our time to O of n. Then, briefly outline your plan before writing any code by minute 5. Doing this shows highly structured thinking, proving to the interviewer that you aren't just blindly memorizing solutions. To hit that timeline, you need to lock in your recognition triggers. Whenever you hear or read phrases like continuous range, cumulative constraint, or frequent queries, your brain should immediately trigger the prefix sum pattern. Train yourself to actively ask, am I calculating a lot of range sums? Can a subarray be expressed using 2 prefixes? If the answer is yes, you've found your weapon. Finally, Section 5, Advanced Dynamic Range Queries. Let's see what happens when our static prefix arrays fail and the interviewer throws a nasty dynamic constraint at you. If the problem involves range sums, but the underlying numbers in the array are constantly being updated, our basic static prefix array is toast. It becomes way too slow. You'd essentially have to take a sledgehammer to your history and rebuild it from scratch on every single update. That takes O of n time per update, which completely ruins our performance. So for these dynamic queries, we have to escalate to trees, specifically Fenwick trees, which are also known as binary index trees and segment trees. Fenwick trees are absolutely perfect for cumulative sums, while segment trees are incredibly versatile for more complex stuff like finding the minimum or maximum in a dynamic range. But look at the massive difference in space complexity here. While segment trees give you maximum flexibility for all sorts of operations, keep in mind they are super memory intensive. They require 4n space, compared to the incredibly elegant 1n space of a Fenwick tree. So Fenwick trees really are the ultimate evolution of the prefix sum when you have to handle updates. By leveraging binary representation, they keep both our point updates and our range queries down to a blazing fast O of log n time, all while maintaining that strict, efficient O of n space. So the next time you see a range query or a continuous subarray, are you going to instantly reach for an O of 1 pre-computed query? You absolutely should. You now have the mental framework to not only recognize but confidently execute these patterns. You know how to eliminate waste, avoid that classic zero index trap, combine everything with hash maps, and even scale up to dynamic trees. But it begs the question, what other hidden data structure patterns are lurking in your interview prep, just waiting to be decoded? Keep learning, and I'll see you in the next explainer.